It's good. A nice recording.
All right. Right, it's already 2 p.m., so we're going to start. Hi, everyone. Today, it's, we have the pleasure to welcome Hubert Le Terme from the University of Grenoble. We'll give a talk on shift invariance for convolutional neural networks.
Thanks, Yassine. Can you hear me?
Yes.
All right, perfect. Yeah, so my name is Hubert Le Terme. I'm a third-year PhD student at the University of Grenoble and at INRIA as well, which is the French National Institute for Research in Computer Science. My supervisors, I have two main supervisors. So they are Valérie Perrier from Grenoble INB, so it's the Institute of Engineering and Management, and Kartik Alhari from INRIA. So he works in the team of Julien Méral in the computer vision team. So my work lies at the intersection between computer vision and image processing. So today I will present a study yet to be published about shift invariance of convolutional neural networks. So during the talk, I will refer to this as CNN. This means convolutional neural networks. So I will start with a short introduction about CNNs. So short overview on CNNs for image classification. And as an example, let's consider a pretty old model called ImageNet. It has been introduced in 2012 by Alex Krzyzewski. So it's a very famous CNN architecture. And as you can see, such a network is built upon a succession of layers through which an input data, so in our case, RGB image, is propagated. And the output is a vector which can be interpreted as a probability distribution over all the possible labels of our task. So in this example, the green layers are linear operators with trainable parameters. And the purple ones are actually fixed and nonlinear operators. So to give an introduction about what a CNN is doing, we first have a look at the two last layers. So I will put them here like this. So this is actually a multinomial logistic regression. So it consists of an affine projection into a C-dimensional space. And in that case, C is the number of labels, followed by a softmax activation. And as an illustration, here, this is an example with 2D input feature vectors. So 2D data points and only two labels. So this is referred to as a binary logistic regression. So during training, the parameters of the yellow boundary hyperplane, which correspond to the green linear layer, a fine layer, are adjusted to get the best possible separation between the two labels. So in this case, it's pretty simple because the data is the data points are separable. And actually, it makes sense only if the feature vectors are drawn from linearly separable distributions, or nearly so. However, for complex data, such as natural images, this property is far from being satisfied. So data are not linearly separable. So the question is, can we do something about it? So in a way, can we transform data in order to make them linearly separable? So in CNNs, the solution found in CNN, which are having quite successful over the past decade, is to design a nonlinear transform with trainable parameters, mapping input data, so input images, to a high dimensional feature vectors. So in this drawing, the input images are represented by capital X, and the feature vectors are displayed as lowercase x. So this transform can be split into a succession of operators, as shown here. So it's a succession of operators with decreasing feature map size and increasing depth. And we refer to these operators as feature extractors. And in order to achieve our goal, which is to make data linearly separable, a good feature extractor must first retain discriminant image components while reducing intra-class variability. So in other words, the feature extractor must push away images belonging to different classes and pull together images with identical labels. So for the rest of the talk, we will focus on the two first layers of the CNN. So this is actually a feature extractor, and it's made on the first convolution layer that you can see here, followed by rectified linear unit and a max pooling. So for the sake of simplicity, we will drop the ReLU. We will only consider the max pooling layer. So first, let's see how this operator performs feature discrimination. So these are the two first layers of the CNN. So each input RGB image is decomposed through subsample convolutions that you can see here with trainable kernels. And in the case of AlexNet, so the example that is shown here, we have 64 output channels, each of which corresponding to a specific convolution kernel of size 11 times 11. So it's a matrix of size 11 times 11. And the subsampling factor is equal to 4. So in this example, hidden feature maps that are denoted as X prime are composed of 64 channels, the size of which is divided by 4 compared to the input images. So input images have the size, in this example, 224 pixels, and the hidden feature maps are of size 56 pixels. Then the resulting feature maps are propagated through a max pooling layer that you can see here, which computes the maximum value over a sliding window of size 3 by 3. And this stage is again performed with a subsampling factor of 2. So again, the size of the output feature maps here is divided by 2. So now we have 64 channels of size 28 times 28. When trained on ImageNet, that is 1 million images and 1,000 labels, we observe that many convolution kernels exhibit oscillating patterns with various scales and orientations, as you can see here. So we have different scales, different orientations. And as such, they are closely related to Gabor filters. So to the left, we have the filters in the spatial domain, and to the right, this is the power spectrum of the filters. So it's the energy of their Fourier transform. So as you can see, each output channel retains features with specific frequency localization. And as such, the first convolution layer tends to discriminate basic shapes such as edges and textures. So I won't spend too much time on feature discrimination, but I will more focus on how the feature extractors reduces intra-class variability. So let's consider again this the first layers of ImageNet, and we take as input a random RGB image and propagate it through these two layers. So let's take this image, for example, and the output, we get 64 output channels here, each of which corresponding to a specific convolution kernel. Now, what we will do is that we will shift. Okay, so this is what I just explained. So input three channels, output 64 channels. Now let's shift the input image by 2 pixels and do the same operation, same transformation with the shifted image. So this is what we get. So those two images are slightly shifted with respect to each other, but you can agree that they should be classified as the same label. And yet the outputs are not exactly the same. Some output channels are similar, that's true, but many other are quite different, despite such a small shift. And this phenomenon may be amplified due to the small size of this image. It's just an example. In real life, we have much bigger images from ImageNet. So here, there are some border effects that should be taken into account. But anyway, this observation raises the following question. How stable are CNN's first layers with respect to small shifts? And before going further, we restrict the scope of the study to oriented and bandpass filters as highlighted here. And it's worth noticing that the other filters, the low-pass filters, are usually quite shift invariant. So the filters that may concern us, that may be problematic, are actually bandpass filters, such as those ones. So why those filters may be problematic? So it turns out that subsample convolution with bandpass filters may lead to instabilities. And I will give a simple example in 1D. So this is an image from a paper from Kingsbury about the dual tree wavelet transform. But anyway, this is a 1D example. And we have just a simple impulse signal, which is all values are equal to 0 except 1. And we shift this signal by a few pixels only. So as you can see, the two signals are very similar, just a few pixel shift. And then we perform a subsample convolution with a high-pass filter. So in this case, it's a discrete wavelet transform, but never mind. And then we get two different interference patterns. So as you can see, despite the input image being very, despite the input signals being very similar, the output signals are very different.
May I ask a quick question?
And this wouldn't happen if the signal wasn't subsampled. So this is really a property of subsampled convolutions. Now, let's delve into our theoretical results about shift invariance.
Can you hear me? No, maybe it's me.
So here, just to give an intuition about what we are doing. So we consider the discrete Gabor-like filters of ImageNet. So those ones. So here is the power spectrum. So it's in the frequency domain. And we denote those filters by capital V. So as you can see, those filters in the Fourier domain, they are represented as two bright spots, which are symmetric with respect to each other. So the distance between the two spots gives you the, yeah.
Can you hear me? Maybe
I was also,
maybe I am hard to, maybe my voice is not, you know, is it, can you hear me or?
yes.
Okay, I was just gonna say, what if we do, let's say, some sort of data augmentation in the sense that, let's say, we train with, let's say, shifted images in the first place? You know, basically this way, the representation may be a bit more robust because of the way we train. So basically, when you will just augment artificially your data set by shifting images. Do you think in that case the filters look a bit, you know, more robust?
Actually, that's what we are doing when training with ImageNet. For example, we perform data augmentation.
Mm-hmm.
But the filter robustness, how can I answer? Well, your question is if you perform data augmentation, every shifted images will be taken into account during training, and therefore it should be quite robust, right?
Maybe. I mean, I'm just thinking it may be. In some cases, there is some success of this, you know, but not always. So it probably depends on the data set. But there are some formulations that try to do it.
Yeah.
Basically, if your problem becomes symmetric, right, then your solution inherits some sort of symmetry too.
Okay.
Is it the case for like large data sets in practice?
So for some sort of convex problem, right? Let's say if you have least squares, if you have perfect symmetry in the, you know, in your data, you will recover some sort of symmetry in the solution too. But for non-convex problems, you know, it's not clear because when you do data augmentation, you change the problem, right? And your algorithm may find a total different solution, which may not work in terms of training. So you do train, but you find different solutions. But I think there was a paper by Miao He. She's like an optimizer, but she thought about formulating this as a two-level stochastic program where the first layer is the expectation, just like in statistical learning. The second layer is another random rotation. So it becomes like a two-layer stochastic kind of program. But most likely, you know, those, I don't think, you know, those are like super successful. Probably it's just they are doing something a bit more naive.
Okay. Well, I would be interested in seeing this paper.
Sure. I will try to find it. They call it composite optimization because it has two layers. And the paper is by Miao He, published in SciOpt. But I will try to find it and send it to you as well. Mm-hmm. But they are not, you know, image processing guys. So most likely, you know, they tried like a, you know, naive data set or something like that. They didn't train on VGG19 for sure.
I see. Okay. Okay, so where was I? Yeah, okay. So what I was saying is that when you look at the power spectrum of the filters, the distance between the two dots gives you the value of the frequency, and the orientation gives you the orientation of the filter. And the symmetry is actually a property of real valued filters. So now let's consider the analytic versions of these filters. So I will plot them here. And we denote those filters by W. So what we did here is that we just set half of the frequency plane to 0 and kept only one half of the frequency plane. So actually the real valued filters here are the real part of the complex valued filters that are displayed here. So here we get complex valued filters with high frequency resolution. And this is interesting because unlike real valued kernels, such filters are well known to produce stable signal representations. It's stable when we compute the modulus of output feature maps, actually, and in particular shift invariance. So therefore, the question is, can we somehow transfer this stability property that we observe on, and that we can prove on analytic signals to the real valued signals that are here, to the real valued kernels? Can we somehow transfer this property? The intuition is that the nonlinear max pooling layer that we add on top of the convolution layer may actually help recovering the shift invariance. And to assess this hypothesis, we apply the following methodology. So first, let's consider the standard setting. So this is the setting which is found in standard CNNs. And it's made of a convolution layer followed by max pooling, as I said before. So we actually consider a simplified version of this feature extractor applied on grayscale input images. So I won't go too much into details about that, but it can be extended to color images. And the exact formulation of this feature extractor is given here. So we perform subsample convolution with a real valued filter, so the real part of W, and then we perform max pooling. And max pooling is, as I said before, the maximum value over a grid of size, well, in many cases of size 3 by 3. So we will refer to this feature extractor as R max feature extractor. And for the sake of visual understanding, they will always be represented with a blue color, light blue color. And now let's replace this feature extractor by another one. It's this feature extractor, which is not found in real life CNNs, but it's kind of a proxy for the Rmax feature extractor. So this one is composed of a complex convolution followed by not a max pooling, but followed by the modulus operator. Again, here we have the mathematical formulation of this operator. So it's a convolution with a complex filter this time, with subsampling, and then we apply the modulus to the feature maps. And we refer to this feature extractor as a C-mod operator, and it will always be displayed with a magenta color, just for the sake of clarity. So we can notice that both outputs, the output of both operators, are of the same shape. So in the case of ImageNet, it's 64 channels, and the output feature maps are of size 28 times 28. So it's divided by 8 with respect to the input images. So the roadmap is as follows. First, we want to show that the output of the C-mod operator is stable with respect to small input shifts. And then we want to prove that under additional conditions, the two feature extractors here produce similar outputs. So by transitivity, we can deduce that the Rmax feature extractor is also nearly shift invariant. So in this talk, we will just assume that the output of C-mod is stable. I won't go into details about that, but let's just assume that this operator is stable with respect to small shifts. What I will try to, what I will explain here is how we want to show that under specific conditions, the outputs of the two operators are closely related. So in other words, we want to show that, so this is the mathematical formulation. So let's start with a few notations in the discrete framework. So kappa here denotes the Fourier window size, and xi denotes the center of this window. So then we consider G of xi and kappa as the set of discrete filters with Fourier transform supported in this window, a window of size kappa centered in xi. So throughout the presentation, I will refer to such objects as discrete Gabor-like filters, as written here. So here is an example. So the left plot represents the power spectrum of such a filter. So we can see that the center of the window is here, it's xi, and the window has this size here. And to the right, this is the filter in the spatial domain, and we have here the real part of the filter, and here the imaginary part of the filter. And the imaginary part is approximates the Hilbert transform of the real part. And as we will see later, the discrete problem, as introduced here, can be reformulated in the continuous framework. And this is much more convenient, actually. So to do so, we consider the following notations. So for a given sampling interval S, we denote by U indexed by S the space of smooth 2D functions with the Fourier transform supported in a square window centered in 0. And the size of the window depends on the sampling interval. So similarly to the discrete framework, we denote by capital V, calligraphical V actually, the set of 2D functions which are supported in a window of size epsilon centered in nu. So as before, I will refer to these objects as continuous Gabor-like filters. It's not exactly Gabor filters, but it's closely related. And here is an example with S equal 1. By design, this filter is actually the only one belonging to US from which the filter introduced here is uniformly sampled at interval S. So this is guaranteed by a sampling theorem, which is called the Shannon-Whittaker theorem. And this theorem actually provides a bound between the discrete and continuous worlds. So to be more precise, let's consider an input image, which is actually a 2D sequence, because we work with the grayscale images here, and a discrete filter that I will call W, a bandpass filter with complex values. So the Shannon-Whittaker theorem states that there exists a unique function f and filter psi, from which x and w are uniformly sampled, such that the discrete and subsampled convolution of x with w is equal to the continuous convolution of f with psi. And moreover, the Fourier transform of psi is supported in a region of size kappa here, divided by s, centered in psi divided by s. So in other words, psi is a continuous Gabor-like filter, such as illustrated here. So in this example, if this is W, the corresponding psi is this filter. Okay, so just tell me if this is not clear. I can try to explain it a bit differently. So before proving equivalence between the two operators in the discrete framework, we will first consider a closely related problem in the continuous framework. So we want to show that the maximum value over a sliding window of the convolution with a real values filter is approximately equal to the convolution with a complex valued filter as shown here. So I will just give us a very quick sketch of the proof, which is adapted from Irene Walsberger's PhD thesis. So we consider a low frequency modulation of f convoluted with psi, which we denote by f0. Yeah, so why we are doing this? This is the power spectrum of f convoluted with psi, and this is the power spectrum of f0. Why we have that is because the modulating a signal in the spatial domain is equivalent to shifting its Fourier transform. So since f0 is a modulation of f convoluted with psi, its Fourier transform is actually a shift of this Fourier transform. So that's why f0 has a low frequency. So now we use this low frequency property of f0 to prove this approximation. So the cosine term here, which is denoted by G, depends on the filter's characteristic frequency nu, as shown here, a vector h, and eta, which is the phase of f convoluted with psi. Now we consider the maximum value of this over a window of size r. And then we get this approximation. And if the window size is big enough, we can see that since G is a periodic function, the maximum value over the window is equal to 1. And then we get our result. We get that the output of the blue, the max pooling operator, is approximately equal to the output of the modulus operator. So then we get our result in the continuous framework. Now the question is, how do we transfer this to the discrete framework? So this is the continuous framework. And now let's move to the discrete framework. So according to the Shannon-Whittaker theorem, as I showed before, the two outputs, the outputs of Rmax and Cmod operators, can be expressed in the continuous framework like this. And besides, using the same reasoning as before, using the low frequency property of f0, we get the following approximate result. And therefore, if we plug these equalities into this approximation, we get this formula. And we can see that unlike the continuous framework, here the maximum value, instead of computing the maximum value over a continuous window, we compute the maximum value over a grid, a discrete grid, with a finite number of points.
So what was G here?
As a visual example, let's consider those examples. So in these figures, G, so the periodic function G, is plotted as 2D is plotted in 2D for 3 different characteristic frequencies. So here we have 3 examples. Yeah. Yep.
What is the function G here?
Okay, so G is this function here.
Okay.
So it's a cosine value. It depends on the characteristic frequency of the filter. It depends. So we evaluate G on a window. So H are the different vectors belonging to this window, and eta is the phase of F convoluted with psi.
Okay. Got it.
So the idea is that we want to evaluate the maximum value of G over a grid. If the maximum value is equal to 1, then we get our equivalence between the 2 operators, as you can see here. This is the output of the max pooling layer, and this is the output of the modulus layer. So, so we would like, ideally, we would like this maximum value to be equal to 1. So when we look at some examples, we see that if we take a random value of characteristic frequency, we can see that 2 evaluation points here are close to a ridge. That means that the maximum value of G over the discrete grid is close to 1. However, there are some pathological cases, as plotted here. So this smileys. In those 2 examples, all the evaluation points fall into pits, actually, as you can see here. So we are never close to 1. This would be different if we had evaluated the maximum value over the continuous window. This happens because we only considered a few data points. So just to point out that the middle and right examples have been specifically designed as failure examples, but most of the time we can find some evaluation points which are close to ridges. So the pathological examples suggest that near equality between the 2 operators cannot be obtained with absolute certainty. Therefore, we introduce a probabilistic framework in which the input image is considered as a discrete stochastic process. And the quantity of interest is the following one. So it's a random variable, actually, and is defined as the Euclidean norm of the Euclidean norm of the difference between the outputs of the 2 operators, normalized by the Euclidean norm of the modulus operator. And one of the main contributions for this work is to show that the expected value of this random variable can be approximated by a quantity which depends on, first, the filter's characteristic frequency, psi, and the subsampling factor, d. So here I will show some examples of an approximation of this expected value. So the left image approximates the expected discrepancy between Rmax and C mod operators with a subsampling factor of 2, and the right image show the same thing, but the difference is that here the subsampling factor is equal to 4. So typically in ImageNet, so the CNN that I showed before, the subsampling factor is equal to 4. So we are in this situation. But for ResNet, for example, the subsampling factor is equal to 2. So we are in this situation for ResNet. So we can see that depending on the filter's characteristic frequency, we can have some very good very low expected values, but you can see that there are some dark spots here, and those dark spots correspond to frequencies for which the output between the two operators can be very high. So they basically correspond to the pathological examples that I showed before. So this is the theoretical part, and we also experimentally assessed this study by considering the dual tree wavelet packet transform. So it's a special. So we implemented CMOD and Rmax operators based on this transform. So in this framework, the subsampling factor D and the window half size kappa depend on the decomposition depth J, which is equal to 2 or bigger. So I won't go too much into details for this transform, but just for you to know that the subsampling factor is equal to this quantity, and the window size is equal to the quantity. So if the subsampling factor increases, then the Fourier window size decreases actually. And what is interesting to notice is that if we consider the complex conjugates, the whole frequency plane is covered by this transform. So because of that, we can recover the input signal, the input image, from the dual tree feature maps. So in this example, I took an example with J equal to, so 2 levels of decomposition. So in that case, input images are convolved with 32 discrete Gabor-like filters, with a window size of pi/4 and a subsampling factor of 2. So we have 32 complex filters. So that's why here each filter is represented by their real part and their imaginary part. And here is the power spectrum, the Fourier domain. So this provides a convenient framework to evaluate our theoretical results. So the experiment setting is, so the data set, in the data set, we used 50,000 images from the ImageNet validation set. And for each dual tree filter and each input image, we compute this quantity. So this quantity is the expected, is the discrepancy between the two outputs. And it's actually a realization of the previously defined random variable. And in addition, we also computed the shift invariance of both operators by considering 2 patches of each input image shifted by 1 pixel along the x-axis. So we consider only a 1 pixel shift and then compute the discrepancy between the two outputs.
Can I ask a quick question here?
And finally, we average this quantity of
Hubert, could you hear me?
Sorry, there is a question?
Yeah. Just maybe the typo, but I just want to ask, like at the mu max n, the divider there, does it have to be C2dxn or it should be RDxn?
Here
the definition, is it a type?
Yeah, no, it's not a typo. It's a good question actually. We could have.
I'm closing the.
Sorry. We could have chosen to divide by this one.
Mm-hmm.
But this choice is because this output is much more stable. So it doesn't depend on. It doesn't matter actually. You can take a shifted image, and this quantity will be the same. We can prove that we can prove that the output of the modulus operator, if you shift your image and compute again the output, they will have exactly the same energy. So for stability reasons, we choose to normalize by this quantity.
Okay. Okay, fair. Thank you.
No problem. And this is the results. But just to mention that I tried both actually, and the experimental results are not that very different. It's just for the sake of stability. So here I plotted again the theoretical results. So it's the expected discrepancy between the Rmax and the CMOD operators. And here is the experimental results on dual tree filters. So each pixel corresponds to a specific dual tree filter characterized by frequency. So as I said before, the dual tree wavelet packet transform covers the whole frequency plane. So that's what we observe here. So the whole frequency plane to each pixels here, there is actually one dual tree filter. So I performed the experiment with j equal 2 and j equal 3, which corresponds to a subsampling factor of 2 and 4, as I said before. So we can notice a strong correlation between the theoretical expected discrepancies and the measured quantities. And in particular, you can see that the pathological frequencies here are correlated with high discrepancies in the experimental setting. And we can observe this for both cases when we have the j equal 2 and j equal 3. So this, now we want to see if this has an impact on the stability of the operators. So first, let's consider the shift invariance of the CMOD operator. So as expected, this operator is very stable with respect to small shifts. So regardless the frequency, we have very high stability. However, when we look at the Cmax operator, we see that some filters are quite stable, but some other are unstable with respect to small shifts. And these regions of instabilities are exactly correlated with the theoretical pathological frequencies. So we can say that instabilities arise when the discrepancy between CMOD and Rmax operators is high. So therefore, we have established a validity domain for shift invariance of Rmax feature maps, such as implemented in standard CNNs. So let's just a quick conclusion. So our contribution is to establish shift inverse properties in CNNs. For that, we have introduced an operator which is a convolution with complex valued filters followed by a modulus, and this actually computes the first layer of what is called a wavelet scattering network. So this is very related to the work of Johan Bruna and Stefan Mala about wavelet scattering networks. However, in standard CNNs, this operator is not implemented. Instead, there is what we call a Rmax operator, which can be found in existing CNNs. But in this work, we have established an analogy between those two operators. And therefore, we were able to establish some invariance properties for existing CNNs. And as future work, we would like to focus also on deeper layer. So could we somehow get cascading Rmax operator in a similar spirit as wavelet scattering networks? Then we would like to study the stability with respect to diffeomorphisms. We have only studied the stability with respect to shifts, but we could also study the stability with respect to rotations, to small deformations. And yeah, I actually forgot to add another point is that as an experiment, we tried to see what happens if we replace the Rmax operator by a CMOD operator in CNNs. And we have observed, well, maybe there's a slide here. We have observed a higher stability, and we actually have observed a slight improvement in the predictive power of the network. So this increase of stability yields an improvement of the predictive power of the network. So this is actually very interesting result. Yeah. So thank you very much for your attention. I don't know if you have questions.
Thank you very much. Let's first upload the speaker over Zoom. Okay, so maybe I'll first let member here ask questions if they have some. I have a question from Bura.
Yeah.
Or maybe Bura, you can go first if you like.
I can go also second, no problem. Yeah.
Okay, maybe then let me ask quickly. So thanks for the very interesting, nice talk. So I guess probably because the CNNs are working reasonably, I mean, there is no need to change the max pool operator. But I was curious, let's say if you change the max operator with something else, is it possible to use some sort of sampling theorem and show that it is related to some sort of complex operator? So here you are using that the max operator can be represented in the complex domain, right? But if it's a softmax or something else, then will you still have some sort of complex filter if it's not max?
Actually, the softmax operator is used at the end of the network, but it's computed on feature vectors, so it's not images anymore. So I'm not sure actually how this can be. This can be.
I mean, I was just thinking. So basically, if you use the max pooling, right? If you use the max pooling, by nature, you will get this bad frequencies.
Yeah.
Right.
Exactly.
So then one question is, one can say, well, the existing stuff is working well, so let's not touch it, right? That's option one. Option two, one may say, what if I replace max with something slightly different, right? Maybe, with some other operator that looks like a max.
Okay.
Maybe like a weighted max, right? So for instance, then most likely, if there's any complex filter, these spots that you have issues, right, may exist in maybe in other spots, or maybe may not exist if you were to replace max with something else, right? So
yeah,
but I don't know, probably you are already using some very special structures, so probably if you change max with something else, maybe you may not, you may lose all the kind of nice properties. I don't know, but
well, actually the max pooling here really how can I say that here,
just as a side remark,
yeah,
the softmax can be actually the Gumbel trick. We can get a softmax by getting a max over a perturbated version of the data. So playing on noise may be a way to actually reuse the transformation that we have for the max and get like an approximation for the softmax maybe. Yeah.
So about the question, can you turn off the sound?
Yeah.
Because I hear myself. It's a bit disturbing. I think what the max is doing here is really to try to find the ridge in the oscillating pattern. So when you reach this maximum value, you don't have any well, all your information is on the real part of your data when you reach the maximum value of the pattern. So I think that's kind of what the max pooling is doing. It's a trick to recover shift stability by simulating the modulus of a complex convolution. But I don't know if this answers your question, but we tried actually to replace the max pooling layer by a modulus and see what's happening. So we replaced the real valued filters by complex valued filters and the max pooling layer by a modulus. And this yields interesting results actually, because we have a higher stability and we have, at least for Alexis, we have an improvement in the prediction.
Right. So basically when you take a max, right, let's say it's an operator that applies to a vector, right?
What applies to vectors?
So basically when you take the max on a 3x3 grid,
yep,
it's an operator on a vector, right? So you have 9 elements. Max is an operator of this 9 elements, right? But let's say if you were to do softmax, right? It is another operator.
Yes,
it won't give exactly the max of it, but will give you something very close to it, right? Maybe if let's say the maximum is 9, you will get 8.5, right? So it will be like a little bit like doing smoothing in the time domain.
All right.
Most likely, it will have some localization property in the Fourier domain, right? But it won't be C mode filter you have, but it will be some variant of it, right? Maybe slightly more localization in the Fourier domain. So then most likely these dots that you have will occur in different places, right? So like when you look at the discrepancy, you see some dots in the frequency domain, right? So it may change them. It may actually make them worse, or it may make them better. So I can't judge. But anyhow, I think here the point is max pooling is already working great, so we don't have to change it. So then let's try to prove something about it. And because the complex stuff is more user friendly to work with analytically, so then the point here is maybe to sort of approximate the real kind of filters, a complex one, and I can see why this is really helpful. So okay, thanks. That's all my question.
Okay, but it could be interesting to try the softmax maybe.
Yeah.
There was a question maybe from Bura.
Yeah, I can actually. Maybe it's not a question. Yeah, it's like curiosity, you can say. So I was really wondering if you have tested, make these experiments on like other types of invariant, like the shifts in the data. Like, have you considered, or like have you tested these kind of methods on like rotations on the data? I was curious, since you did all these experiments. Were you able to test C mode on the rotations or other kind of translations that you might have on your data?
I haven't done it. Sorry.
Yeah, please. And I have another follow-up question after this, actually.
No, I haven't done it, but this is. I hope I will be able to do it before the end of my PhD. Actually.
Okay. Yeah, because
just maybe to give a more precise answer. with scattering networks, I think that they have proved some stabilities with respect to other types of transformations, such as rotations and deformations, and this is controlled by the Jacobian of the diffeomorphism, I think, and but we don't want to be too invariant, because, for example, if you take a very simple example on MNIST, you don't want a 6 and a 9 to be classified in the same category. So you want stability. You don't want full invariance.
Yeah, I totally understand. Yeah, depending on your problem, of course, you might want to have some like additional properties. But yeah, following up on that, I was very curious about like does the theory of this one some clues about how you can extend these results for the other type of rotations, or like does it like do you see any kind of a potential to use this kind of theoretical results that you have used to prove your results for the shifting to have like a more general implications for other type of invariants in your problem? Because I know like the complexness is like a really deep kind of a literature. Like, is it possible to see that kind of a direction? Just kind of out of curiosity, I'm asking.
I'm not quite sure, but I think you can use well, the deformation in the discrete domain can be I think you can use the sampling theorems to reformulate your problem in the continuous domain, and then you get diffeomorphisms.
I see.
However, I don't know if we can get this kind of similarities between the max pooling and the modulus operators. So I would be curious to do that, but I'm afraid I don't really know how to answer that.
Yeah, I mean, I just want.
I guess that we can get some sort of equivalence, but I'm not 100% sure.
I see. Thank you so much again. Really interesting topic.
Thank you for your attention.
I had maybe one or two more questions. So most of your talk was dealing with black and white images, right? But you had mentioned that you could extend it to RGB setting. Or you did it in the paper, like
yes.
What was the problem and how did you?
No, it's not a problem. It's just that we can extend this to RGB images, because here, so you can see that the bandpass filters are grayscaled here. So that means that this can be equivalently reformulated as first you mix your three RGB patterns with trainable mixture parameters, and then you get one grayscale image.
Oh, I see. Okay.
And then you can apply this, and we can show that, and we can measure actually this level of equivalence. This is because we have almost grayscale filters here.
I see.
And actually, this is related to some color space, like YCC color space. I don't know if you're familiar with that. But when you mix your color changes with positive weights.
Yeah, but I've used
it. Get a luminous
channel. Yeah, I actually, I get it. Okay.
And this is how it can be extended.
All right, thank you so much. Thanks again for. Okay, I'm gonna put the sound again. Thanks again for attending. And very nice.
Yeah, you're welcome. Thank you very much.
Thanks for the talk. See
Yeah,
you.
thank you for the talk.
See you in future occasions. Yeah.
Okay.
Thank
Bye.
you. Thank you. Bye bye.
All right.
Thank you for the talk. Bye.
You.